Here is the question that I posed at the end of the last part of the lecture, and most of the difficulties that students have with a question like this have to do with not understanding what each quantity represents. So let's go through it, focusing on that. So we have an initial time of 2 seconds and a final time of 5 seconds, and so that gives us a delta t, a time interval of 3 seconds. And let me just collect everything together. So now we have an initial position, a velocity, and a delta t. And we're going to use this relationship that we just found to find the final position. So I'll work in parts. V delta t is just v, where I've multiplied each component by 3 seconds. And now I just have a vector addition to do, and 2 plus 3 is 5, and 7 minus 6 is 1, and so the answer is C. Let's finish up by talking about perspective. Suppose a car is driving along at 30 meters per second, and it's 100 meters away from a police officer who's using a radar gun to measure its speed. The radar gun just measures the distance at different times and then does a simple distance traveled by time calculation to arrive at a speed. So in 1 second, the car goes from 100 meters away to 70 meters away, and I think you'll agree that according to the police officer, the speed of the car is 30 meters per second. At the same time, you're coming in the other direction at 30 meters per second, and you're also measuring the speed of the oncoming car with a radar gun. Of course you are. Doesn't everybody have a radar gun in their car? Well, notice that in 1 second, the distance to the oncoming car decreases from 200 meters to 140 meters. And so your radar gun is going to inform you that the oncoming car is going at 60 meters per second. This illustrates that measurements of speeds and velocities depend not only on the motion of the object being measured, but also on the perspective of the person doing the measurements. This idea of being able to view the motion of one thing from the perspective of another moving thing is going to be important to us. And so it's time to meet the idea of relative velocity. So let's say you throw a ball to the right at 15 meters per second, and I'm calling right our positive x direction. Let's say your friend Spaceman Spiff is going left at 20 meters per second, and your other friend Trogdor the Burninator is going right at 20 meters per second. Let's talk about what the velocity of the ball is according to Spiff and according to Trogdor. Well, so we need some velocity vectors. According to you, standing stationary on the ground, the ball is going right at 15 meters per second, and so that's 15 I hat meters per second. 15 meters per second in the positive x direction. Spiff is going 20 meters per second in the negative x direction, so negative 20 I hat meters per second. Trogdor is going 20 I hat meters per second. Well, so Spiff sees the ball going to the right, so in the positive x direction, at 35 meters per second. You can probably convince yourself of that. And so I'm going to call that v sub sb. And so it's 35 I hat meters per second. And these subscripts, the second subscript is saying that this is a velocity of the ball. And the first subscript is saying that this is the velocity relative to Spiff, or as seen by Spiff. So this is going to be my convention. The first subscript is what this velocity is relative to, and the second subscript is what this is the velocity of. So Trogdor, according to Trogdor, well, he's catching up to the ball at 5 meters per second, and so he sees it going to the left at 5 meters per second. Now, look at how you can calculate these. Play around with the vectors, and you should be able to convince yourself that that VSB is just the velocity of the ball minus Spiff's velocity, and that VTB, the velocity of the ball relative to Trogdor, is the velocity of the ball minus the velocity of Trogdor. This then is going to be our definition of how we calculate a relative velocity. A relative velocity of some object 1 relative to an object 2 is just the velocity of 1 minus the velocity of 2. And you can think of that as the velocity of object 1 as seen by object 2. Notice there's a difference here. And despite this being a difference, this is not a change. We're not talking about one physical quantity and a difference between a final value and an initial value. We're talking about two velocities, which are velocities of different objects, but at the same time. And so even though it's tempting, it looks like, because it's a subtraction, this might be a delta something. It's not, because a delta means a change, and this thing isn't a change. Sometimes, especially once we start talking about energy later in the course, we're going to be less interested in the relative velocity and more interested in the relative speed, which is just the magnitude of the relative velocity. So let me just talk a little bit about how to calculate that in more detail. So notice we can expand those velocities out in terms of their components, and the way we calculate a magnitude is by a Pythagorean theorem, and so putting those together, that gives you this relationship for relative speed. Don't memorize this, you can always get this just from definitions. What I want to show you, though, is that there's a useful special case in one dimension. So suppose the y components are all 0, then that reduces to this, where all that's happened is that the y components have disappeared, and a square root of a square just means you're dropping any negative sign, and so it's an absolute value. And I want to stress that this is only true in one dimension. Let me just show you a quick example of this. Suppose we have two airplanes moving as shown, and we want to know the relative velocity and speed. I'll just say an air traffic controller would be quite interested in the relative velocity, because if the relative velocity vector points along the line connecting the planes, that tells them these planes are going to collide. So we're going to calculate it using the definition of relative velocity that we've just come up with. And note that that corresponds to this drawing. Given that you know how big these two vectors are, you might see that you can immediately, very quickly, write down what the relative speed is. But let's calculate it. So that gives us a relative velocity, which is just this subtraction, and we simply take the magnitude of that to get the relative speed.